In the beginning, before the universe was mapped by our equations, before galaxies were charted with the rigor of mathematics and the poetry of human longing, there was only the endless darkness. In that darkness, the mind of humanity has always sought points of light, truths, mysteries, moments of revelation scattered like constellations across the void. Some of these lights are familiar: the gentle glow of a nearby star, the measured spiral of a galaxy, the sharp flash of a supernova's death throes. Others are stranger, slipping always just out of reach. In the cold, silent halls of cosmology, one such enigma flickers: the white hole. A white hole is perhaps the most paradoxical child of Einstein's equations. It is a theoretical object, birthed not from observation, but from the relentless logic of mathematics. To imagine a white hole, one must first understand its twin, the black hole, that voracious maw that eats light, time, and matter, from which nothing can escape. The black hole is a region of space where gravity has become so powerful, so utterly dominant, that it severs itself from the rest of the universe, creating a one-way door, in, but never out. But for every door that closes, might there be one that opens the other way? The equations that describe black holes when run backward in time yield a mirror image: a white hole. Where a black hole devours, a white hole expels. Where nothing can escape a black hole's embrace, nothing can enter the dominion of a white hole. It is, in theory, a region of space and time from which matter and energy erupt outward, but into which nothing may ever return. This is not merely a poetic inversion. It is a solution to Einstein's field equations, written in the language of general relativity in the mid-20th century. The mathematician Igor Novikov, the physicist John Archibald Wheeler, the Soviet theorist Yakov Zeldovich, each in turn gazed upon the equations and saw the shadow of this impossible phenomenon. The Schwarzschild solution, the simplest answer to Einstein's question of how mass curves space-time, contains both a black hole and a white hole, joined at a singularity, a point where the known laws of physics break down. Yet unlike their dark siblings, white holes seem to be absent from the sky. No telescope, however sensitive, has ever caught the unmistakable signature of a white hole's outpouring. They remain theoretical, existing more firmly in the realm of mathematics than in the world of measured phenomena. Still, the possibility of their existence gnaws at the edges of our understanding. If they exist, white holes could rewrite our conception of time, causality, and the structure of the cosmos itself. To understand why scientists are so compelled by these mathematical phantoms, one must journey into the heart of theoretical physics. The story begins, as so many do, with a question: what happens at the edge of a black hole? In 1916, Carl Schwarzschild provided the first exact solution to Einstein's field equations, describing the space-time geometry outside a spherical, non-rotating mass, the Schwarzschild metric. This solution gave us the event horizon, the surface beyond which nothing returns. Reverse the arrow of time, and the equations remain valid, but the scenario changes. Instead of a point where matter falls inward, never to be seen again, we have a point from which matter explodes outward, never to be recaptured. The white hole is the time-reversed black hole. This symmetry is not mere mathematics. It is a profound statement about the nature of time. The laws of physics, at their most fundamental, do not distinguish between past and future. They are time-symmetric. If a process is possible in one direction, it is possible in the other. Yet our universe does not appear to share this symmetry. We see stars collapse into black holes. We do not see white holes spewing matter into space. Where, then, are the white holes? Are they hidden, or simply forbidden by some deeper law? The question burns brighter when we consider the nature of singularities. A singularity is a point where density and gravity become infinite, where the fabric of space and time is pinched into a dimensionless point. In the heart of a black hole, hidden from view by the event horizon, lies such a singularity. The mathematical extension of the Schwarzschild solution tells us that, connected to this singularity, on the other side of a wormhole throat, lies a white hole. This structure, known as the maximally extended Schwarzschild solution, was mapped in detail by Martin Kruskal and George Sekaris in 1960. The resulting Kruskal diagram charts not just a black hole but a white hole, two universes, and a bridge between them, the Einstein-Rosen bridge, known more colloquially as a wormhole. Yet this cosmic diagram is not the universe we observe. Black holes, we know, can form from the collapse of massive stars, a process seen in supernovae and inferred from the gravitational waves detected by LIGO and Virgo in 2015 and 2017. White holes, however, do not seem to have a corresponding formation mechanism. There is no known astrophysical process that would create a region of space from which matter spontaneously erupts, without any prior cause. Still, the possibility lingers. In the early days of general relativity, theorists speculated, if the universe began in a singularity, the Big Bang, could that singularity have been a white hole? Could our entire observable universe be the outflow of a white hole in some larger, unknowable cosmos? The physicist Stephen Hawking, the cosmologist Roger Penrose, and the Nobel laureate George F. Smoot all grappled with the nature of cosmic singularities. The Big Bang, after all, is mathematically similar to a white hole, a point from which matter and energy erupt into space and time. But there are differences. The white hole of the Schwarzschild solution is eternal, existing for all time in the equations, while the Big Bang is a single, unique event, the beginning of both time and space as we know them. The analogy, though suggestive, is incomplete. Despite their absence from observation, white holes have become a playground for theoretical exploration. In the 1970s, as the laws of thermodynamics were applied to black holes by Jacob Bekenstein and Stephen Hawking, new paradoxes emerged. Hawking showed that black holes are not truly black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. Over unimaginable spans of time, black holes can evaporate, shrinking and fading into nothingness. But what happens to the information that falls into a black hole? Is it lost forever, violating the fundamental tenet of quantum mechanics that information is preserved? Or does it somehow escape, perhaps through a white hole? This is the so-called black hole information paradox, a question that has haunted physicists for 5 decades. In 2014, Carlo Rovelli and Francesca Vidotto proposed a radical solution. Perhaps as a black hole evaporates, it transforms into a white hole. In their model, based on the principles of loop quantum gravity, the collapsing core of a black hole does not vanish into oblivion. Instead, quantum effects halt the collapse at a minimum volume, causing a bounce. The black hole becomes a white hole, and matter is expelled, albeit after an astronomical delay far longer than the age of the universe. This idea, though speculative, offers a tantalizing resolution to the information paradox. Nothing is lost, only delayed. The mathematics is intricate, involving the quantization of space-time itself. In loop quantum gravity, space is not a continuous fabric, but is woven from discrete loops of quantum geometry, each a tiny spin network at the Planck scale. As a black hole collapses, these quantum effects become dominant, preventing the formation of a true singularity and triggering the transition to a white hole. The details remain a subject of intense debate, but the possibility has reignited interest in white holes as more than a mathematical curiosity. If white holes exist, what would they look like? The answer is as strange as the question. A white hole would appear as a region of space from which matter and light pour outward, but into which nothing can enter. From the outside, its event horizon would look identical to that of a black hole, impenetrable, mysterious. Only by observing the outflow of matter could an observer distinguish between the two. No such outflow has been seen, but some astronomers have suggested that certain unexplained phenomena might be white holes in disguise. In 2006, a brief, intense burst of gamma rays was detected by NASA's SWIFT satellite, GRB 060614. Lasting 102 seconds, it did not fit the profile of any known supernova or neutron star merger. Theorists speculated, could this be the signature of a small white hole, releasing its pent-up energy in a single burst? Later analyses favored more conventional explanations, but the possibility remains. Some of the universe's most enigmatic flashes might be the dying breaths of white holes. The notion of white holes intersects with another of astrophysics' strangest ideas, wormholes. In the maximally extended Schwarzschild geometry, the black hole and white hole are connected by a throat, a shortcut through space-time. The idea was first articulated by Einstein and Nathan Rosen in 1935, and later popularized in science fiction as the traversable wormhole. a tunnel that allows faster-than-light travel between distant regions of space. But the white hole end of the wormhole is inherently unstable. Any attempt to traverse it would cause it to collapse. The possibility of stable, traversable wormholes remains a subject of speculation, explored in the 1988 work of Kip Thorne and Michael Morris, but forbidden by the classical laws of physics. Still, the mathematics persists, haunting the edges of what is possible. In the quantum realm, where uncertainty and probability reign, new possibilities emerge. The holographic principle, articulated by Gerard 't Hooft and Leonard Susskind, suggests that the information content of a region of space can be encoded on its boundary, an idea inspired by the entropy of black holes. In this view, perhaps the white hole is not a physical object but a boundary condition, a mathematical necessity that ensures the conservation of information. Perhaps the universe itself is a kind of white hole, its boundaries encoding the secrets of its interior. The question persists: why do we not see white holes? The most likely answer, according to the majority of physicists, is that they are forbidden by the second law of thermodynamics. The universe has a preferred direction of time, an arrow that points from past to future, from lower to higher entropy. The formation of a white hole would require an extraordinary decrease in entropy, a reversal of the normal flow of time. In this sense, white holes are not merely rare. They are forbidden by the fundamental nature of the cosmos. Yet, as with so many ideas in physics, what is forbidden in practice is permitted in theory. The equations allow white holes. The universe appears to decline the offer. But the search continues, not only in the equations, but in the sky. New telescopes peer deeper into the cosmos than ever before. The Event Horizon Telescope, which imaged the shadow of the black hole in M87 in 2019. The Laser Interferometer Gravitational Wave Observatory, which detects the ripples of colliding black holes. The Vera C. Rubin Observatory, which will soon survey the entire sky for transient phenomena. In these data, some hope the ghostly fingerprint of a white hole may one day be found. To understand the allure of white holes, one must appreciate the interplay of mathematics, philosophy, and observation in modern science. The black hole was once a mathematical oddity, dismissed by Einstein himself as too absurd to exist. Yet today, we have seen their effects, mapped their shadows, and listened to the music of their mergers. Might white holes follow the same path, from abstraction to reality? Consider the analogy of the negative numbers. For centuries, mathematicians resisted the use of numbers less than zero, considering them nonsensical. Yet today, negative numbers are an indispensable tool, their meaning clear and their utility proven. White holes are, in some sense, the negative numbers of spacetime, permitted by the rules, yet elusive in practice. The mystery of white holes also touches on the deepest questions of cosmology. If the universe began in a singularity, was that singularity a white hole? Are black holes gateways to new universes? Each white hole the Big Bang of a baby cosmos? The inflationary cosmology of Alan Guth and Andre Linde suggests that universes can bud off from one another, each with its own laws and constants. The physicist Lee Smolin has speculated that black holes might be the seeds of new universes, their singularities bouncing into white holes in a process of cosmic natural selection. Here, the scientific merges with the philosophical. If every black hole births a new universe, the multiverse is populated by a branching tree of realities, each connected by the hidden throats of white holes. In this view, our universe is both parent and child, part of an endless lineage stretching back through eternity. Yet for all their allure, white holes remain firmly in the realm of speculation. The equations permit them. The sky does not reveal them. They are a reminder of the boundaries of knowledge, the places where mathematics and reality diverge. Still, the pursuit continues. In the quantum gravity laboratories of the 21st century, physicists probe the Planck scale, searching for the signatures of white holes in the patterns of cosmic microwave background radiation, in the afterglow of the Big Bang, in the high-energy flashes of distant gamma-ray bursts. Each search is a testament to the human longing for understanding, the drive to illuminate the darkest corners of the cosmos. It is this longing that makes the study of white holes so compelling. They are not merely objects in space, but windows into the nature of reality itself. They force us to grapple with the meaning of time, the fate of information, the structure of space-time at its most extreme. They are, in a sense, the ultimate what if, a question posed by the universe to those bold enough to seek its answer. In the end, the story of white holes is a story of possibility. They may never be seen, never detected by any instrument, yet their presence in our equations is a sign that the cosmos is stranger than we imagine, that the boundaries of knowledge are always shifting, always expanding. In the darkness beyond the stars, perhaps, a white hole waits, a door not yet opened, a mystery not yet solved. To peer into the mathematics of white holes is to stand on the threshold of the unknown. It is to gaze into the heart of the equations and find, not certainty, but possibility. For in the end, science is not merely a catalog of facts, but a journey into the darkness, a search for the light that reveals the shape of the world. The equations that describe white holes are not simple. The Schwarzschild metric, first proposed in 1916, is the starting point. It is written in the language of differential geometry, the mathematics of curved space. In its static form, it describes a spherically symmetric, non-rotating mass, but when extended beyond the event horizon, it yields both black and white hole regions. The Kruskal-Sekeres coordinates make this structure explicit, mapping the causal relationships between events near the singularity. In these diagrams, the black hole is a region from which no signal can escape to infinity, while the white hole is a region from which no signal can enter from infinity. The mathematics is elegant, but its physical meaning remains debated. Does the white hole region correspond to anything real, or is it an artifact of a particular choice of coordinates? Most physicists believe that the white hole region is unphysical, an idealization that cannot survive in a realistic, evolving universe. The formation of a black hole from the collapse of a star is fundamentally asymmetric. There is no time-reversed process that would create a white hole from empty space. Yet the equations are stubborn. In the language of Penrose diagrams, developed by Roger Penrose in the 1960s, every black hole has a white hole counterpart, at least in the idealized eternal case. The universe, it seems, is richer in possibility than in reality. There are other solutions to Einstein's equations that contain white holes. The Kerr metric, discovered by Roy Kerr in 1963, describes a rotating black hole. Its maximal analytic extension reveals a complex structure, not just a black hole and a white hole, but a sequence of nested universes, connected by ring singularities and wormhole throats. The Reissner-Nordstrom metric, describing a charged black hole, is even stranger, with multiple horizons and regions of spacetime connected in a fractal web. These solutions, however, are almost certainly unphysical. Real astrophysical black holes are neither eternal nor perfectly symmetrical. They are born from the messy collapse of matter, their interiors hidden from view, their singularities cloaked in the secrecy of the cosmic censorship hypothesis. Penrose's weak cosmic censorship conjecture, proposed in 1969, suggests that singularities are always hidden within event horizons, never exposed to the outside world. White holes, in this view, are not merely rare, they are impossible. Yet, as the history of science reminds us, the impossible sometimes becomes real. The black hole was once dismissed as a mathematical fantasy. Today, it is a fact of astrophysics. The white hole remains, for now, a mathematical possibility, a challenge to our understanding, a test of our imagination. The search for white holes is not merely an exercise in speculation. It is a probe of the limits of physical law. It tests our understanding of time, entropy, causality, and the ultimate fate of information. It is a reminder that the universe is not merely what we see, but what we can imagine. In the laboratories and observatories of the world, the search continues. The Event Horizon Telescope, an international collaboration linking radio telescopes across the globe, has imaged the shadow of the supermassive black hole in M87. The Laser Interferometer Gravitational Wave Observatory, using kilometer-scale arms and mirrors suspended in vacuum, has detected the ripples of spacetime from colliding black holes. The Fermi Gamma Ray Space Telescope, orbiting above Earth's atmosphere, scans the sky for the flashes of gamma-ray bursts, seeking the signature of the unknown. In these data, some hope, the trace of a white hole may one day be found. Perhaps in the unexplained gamma-ray bursts, in the anomalous flashes of high-energy radiation, in the patterns of the cosmic microwave background, the fingerprint of a white hole awaits discovery. Yet the search is not only outward, but inward. The equations of quantum gravity, the attempt to unify general relativity with quantum mechanics, may hold the key. In loop quantum gravity, as explored by Ravelli and Vidotto, the singularity at the heart of a black hole may be replaced by a bounce, leading to the formation of a white hole. In string theory, as developed by Edward Witten, Juan Maldacena, and others, the fabric of spacetime is woven from vibrating strings and higher-dimensional branes, with black holes and white holes as possible states. The information paradox, first articulated by Stephen Hawking in 1976, remains unsolved. The holographic principle, the firewall hypothesis, the ER-EPR conjecture, all are attempts to resolve the fate of information in black holes, and each touches in its own way on the question of white holes. Perhaps, in the end, the white hole is not a physical object but a principle, a statement about the limits of knowledge, the boundaries of the possible. Perhaps it is a reminder that the universe is not only stranger than we imagine, but stranger than we can imagine. In the darkness beyond the stars, the white hole waits, a possibility, a challenge, a door not yet opened. To seek it is to embrace the unknown, to journey into the heart of the equations, to confront the limits of understanding. It is to remember that science is not merely a catalog of facts, but a voyage into the infinite, a search for the light that reveals the shape of the world. And so the story continues. In the halls of mathematics, in the silence of the observatory, in the dreams of those who seek to understand, the white hole endures. It is a question, a possibility, a mystery. It is the light at the edge of the darkness, the hope that the universe holds secrets yet undiscovered. In the end, perhaps, that is the true meaning of the white hole, not as a thing to be found, but as a symbol of the enduring quest for knowledge, the drive to illuminate the shadows of the cosmos, the courage to imagine what lies beyond the horizon. For in every question, there is the possibility of an answer. In every darkness, the hope of light. And in the story of the white hole, the promise that the universe is not yet finished with us, that there are still doors to be opened, still mysteries to be revealed, still wonders to be found.